Hello everyone. In this video, I am going to talk about chapter 12, section 14.1 through 14.3. We're going to talk about work and energy. We're going to learn to calculate the work of a force. We'll also learn to apply the principle of work and energy to a particle or system of particles. There are various examples. One of my favorite will always be the roller coaster. So total energy conserved does not change. Okay, let's first take a look at some definitions. Here's another equation for work kinetic problem involving particle can be derived by integrating the equation of motion F equals ma with respect to displacement. So we're going to by substituting at equals v times dv slash ds, dv divided by ds, first derivative of velocity with respect to position, into ft equals mat. The result is integrated to yield an equation known as the principle of work and energy. This principle is useful for solving problems that involve force and velocity and displacement. It can also be used to explore the concept of power. In using this principle, we must first understand how to calculate the work of a force. So definition over here, force does work on a particle when particle undergoes a displacement along the line of action of the force. Force is defined as the product of force and displacement components acting in the same direction. So if the angle between the force and displacement vector is theta, the increment of force du done by the force will be du equals E ds cosine theta. So in other words, in order for the force to do work, that force needs to generate displacement on the same direction as the force. Okay, so that cosine theta is saying, well, in case you have an angle, we're going to break our force vector into parallel to the direction of the movement and perpendicular to the direction of the movement. So the perpendicular direction does not do any work. But however, parallel direction is the parallel component of the force is the component that's doing the work. So we're going to by using the dot product and integrating the total work can be written U work from 1 to 2 from location 1 to location 2 will be integral from R1 to R2 FD dot product dr FDR. So if f is a function of position in a common case, and this equation becomes u from 1 to 2, total work from position 1 to position 2, integral from s1 to s2, f cosine theta ds. If both f and theta are constant, if they are constant, we can simplify this equation into u from 1 to 2, or total work from point 1 to point 2, fc, since it's a constant, cosine theta, and then you have s2 minus s1, the net distance here moving. What's the total distance going from S1 to S2? So work can be positive, can be negative as well. Under the condition that force and the movement are in the same direction, we're doing positive work. Under the condition work and movement are on the opposite direction, then the work will be, we're doing negative work. Okay, so force and the movement, same direction, positive work. Force and movement, opposite direction, the negative work. If the force and the displacement direction are perpendicular, if they're 90 degrees from each other, then this work is zero. Where that force is not doing any work if that force and the movement are on the perpendicular with each other. Work done by a gravitational force on a particle will always be coming down, or sometimes we call it weight of an object. It can be calculated using this equation u from 1 to 2, integral y1 to y2. And notice that y is only in the vertical component. Since gravity is always going down, so whenever we need to calculate how much work is being done by the particle, how much work is being done by the gravity, right? So we're only interested in how much vertical displacement do we have. So we're going from integral from y1 to y2, vertical displacement, and then you have negative w dv. And then there's the u from 1 to 2, it will be negative w y2 minus y1. And there's the negative w delta v. The work of a weight is a part of the magnitude of the particle's weight in its vertical distance. If delta y is upward, so in other words, weight goes down, but however is your particle movement direction, the movement is going up, the opposite direction of the weight, then we're doing negative work since the weight force always goes down. Let's take a look at what's going on with spring forces. When this spring is being stretched, a linear elastic spring develops the force of magnitude Fs equals Ks, and where K is the spring stiffness and S is the displacement from the unstretched position. The work of the spring force moving from position S1 to S2 will be U, work, total work from 1 to 2, location 1 to location 2, integral S1, S2, Fs ds, and also since that Fs spring force will be K times S, kinetic, not kinetic, spring constant times the change of the length, right? How much is being, the spring is being stretched or compressed. So that's what that Ks is. So integral from S1 to S2 Ks ds, that gives me 0.5 Ks S2 squared minus 0.5 Ks1 squared. And if the particle is attached to the spring, the force Fs exerted on the particle is opposite to that exerted on the spring. Thus, the work done on the particle by the spring force will be negative, or U from for 1 to 2, that will be negative 0.5 Ks2 squared minus 0.5 Ks1 squared. It's important to know the following here about the spring forces. The equation above are for linear springs only. Recall that linear spring develops the force according to F equals Ks, essentially equation of a line. The work of a spring is not just the spring force times the distance at some point. For example, KSI times SI. Be aware this is a trap that usually students make mistakes on. Always double check the sign of the spring work after calculating it. It is positive work if the force on the object by the spring and then movement are in the same direction. So principle of working energy says by integrating the equation of motion, you have sigma ft equals mat equals mv dvds. Principle of working energy can be written as sigma u1 to 2, 0.5 mv2 squared, or initial kinetic energy, this T1 right here, let me highlight it, T1 right here, initial kinetic energy plus total work being done to the system equals the final kinetic energy. Okay, sigma u 1 to 2 is the work by all the forces acting on a particle as it moves from position 1 to position 2. Work can be either positive or negative. Okay, T1 and T2 are the kinetic energy at the beginning and at the end. So initial kinetic energy and final kinetic energy. So your T1 will be 1 half mv1 squared, and T2 will be 1 half mv2 squared. Kinetic energy is always a positive scalar velocities because we have velocity squared. So the particle's initial kinetic energy plus the work done by all the forces acting on the particle as it moves from its initial to final position is equal to the particle's final kinetic energy. So we have our initial kinetic energy plus total work that is being done to the system that gives us the T2 total final kinetic energy. Note that principal work energy T1 plus sigma U1 to 2 equals T2 is not a vector equation. Each term here results a scalar value. Both kinetic energy and work have the same unit, that of energy. In the SI system, the unit for energy is called is we use joule. 1 joule equals 1 Newton times meter. In the FPS system, units are in foot pound. Principal working energy cannot be used in general to determine the force directly normal to the path. So in other words, if your force is perpendicular to the direction of movement, if they're perpendicular, then this force is not doing any work. Since this force does not do work, then it does not work this way. Principal working energy can also be applied to a system particles by taking the summation of all the kinetic energy of all the particles in the system and the work due to all the forces acting on the system. In case a body is sliding through a rough surface, we're going to consider this block, which is moving over a rough surface. We apply the force P to the right, pulling the block to the right, just balance the resultant of the friction force, mu k kinetic friction coefficient times the normal force. This gives me the friction force of this block moving on the surface. Okay, a constant velocity v will be maintained. The principal work energy equation says my initial kinetic energy 1 half mv squared plus all the work being done to the system. Now we know that two forces are doing work. Okay, weight and normal force are perpendicular to the direction of the movement. So the W and the N, the weight and the normal force here, they do not do any work. Okay, the two forces doing work. One, it will be the P pulling to the right, and there's also the friction that pulling to the left. So I have the force P times the distance doing positive work because I am moving to the right. Force and the direction of movement are the same. Friction will always be the opposite direction of your movement. So you have negative doing negative work, mu k n times s. That's negative work. Okay, total initial kinetic energy plus all the work being done to the system by the P, by the friction, right? That will equal to the total final kinetic energy. Since we know that this thing is a constant, right? My velocity does not change. If under the condition it's constant velocity, that means this term and this term should be a zero together, okay, because zero point 0.5 v squared is zero point 0.5 v squared on the left, on the right side hand side of the equation. So that means the work being done by P is equal to the work being done by the friction. That will maintain a constant velocity. Okay, so overall, this equation is satisfied if P equals mu Kn. However, we know from the experience that friction usually generates heat, a form of energy that does not seem to be accounted for in this equation. It can be shown that the work term mu K and S represents both the external work of the friction force and the internal work that is converted into heat. Let's take a look at some examples together. We have an inclined plane over here at a 30-degree angle. So when the value of S equals 0.6 meter, spring is not stretched or compressed. And we know the mass of the block is 10 kilogram, which is subject to acceleration to A. Force of 100 Newton has a speed of 5 meters per second down the smooth plane. We're looking for the distance S when the block stops. Okay, we know that's figure out what kind of work is being done to the system. So over here, what we were doing, the 1, 2, 3 here, is figure out we have three different forces, and these three different forces are doing work to the system, to this block. Okay, so we're looking for this is what the 1, 2, 3 is. Okay, so we have that 100 Newton. 100 Newton is pulling the block down, and that is doing work. Okay, so you have 100 Newton times the distance being S2 minus S1, the change of distance, how much distance change. Okay, force times distance, and that 100 is the exact same direction as your movement. Second one is your weight. Okay, weight, we know the mass of the block is 10 kilogram given by our problem, 10 kilogram. Okay, so that 10 kilogram times 9.81, uh, that is the weight of the block. However, weight, we know that it's going straight down. Okay, so we know this angle right here is 30 degrees. So we multiply by sine 30. This will be the component, the part of the weight, 30-degree, meaning part of the weight that is doing work along the inclined plane. Sine 30 meaning the portion that is parallel to the inclined plane is doing work by the way. So 10 times 9.81 times sine 30, and then multiply the change of distance. Okay, weight is doing work, and also the spring work of the spring force. And based on the equation that we learned from the previous slides, you have negative 0.5 times 200 times S2 minus 0.6 square. Okay, and then next thing is going, this 200, if you get confused, 200 is the spring constant, by the way, 200 Newton meter. And then example, keep going. Putting in our equation, we have our initial kinetic energy. We know initially the speed is this much, 5 meters per second. Okay, so we have 1/2 times mass times velocity squared, initial kinetic energy, plus the work being done by the weight, not weight, sorry, the work being done by that 100 Newton pulling down, the work being done by the weight, and also the work being done by the spring. Initial kinetic energy plus all of the forces that's doing work to the system, that gives me the final kinetic energy. And our problem looking for the distance when the block stops. Okay, so when the block stops, kinetic energy equal to zero, and that's why you have a zero on the right hand side, final kinetic energy equal to zero. Using this, we can calculate the value of S2, so how much distance does it move. Okay, hope that helps you. Next example, we have a block coming down 5 feet per second, and it's 2 pound brick is sliced down with a velocity 5 feet per second. And then we're looking for the speed here at location B, and the distance D from the wall to where the brick strikes the ground, and its speed at C. So we're looking for the speed at B, we're looking for the speed at C, and we're also looking for the distance D over here. So using the principle of energy, we know that initially it's 1/2 mv squared, 5 feet per second squared, right? Initially it's this much. And then notice that this thing is on a smooth roof. That means no friction involved. If there's no friction, the only force that's doing work will be the gravity. And keep in mind, it's not um, gravity because it's going down, going straight down. So all we're interested in is vertically how much distance is travel from A to B. So that's why you have a 2 times 15 because it's 15D. We're going vertical direction. So this is how much work is being done by the weight that give us the final velocity. So initial, I'm defining A as my initial, defining at location B is my final. So 1/2 times mass times final velocity, VB squared. That will help me, one equation one I know, that will help me calculate the value of VB. Similarly, we can do it in between A and C. Let me use a different color. Okay, now A is my initial, C is my final. C is down here. So my initial kinetic energy plus all the work being done, again, it's being done by the weight. I have 15 feet plus 35 feet, that is 45 feet. Okay, final kinetic energy will be 1/2 mass times velocity C squared. That will give me the velocity C. Okay. Next thing, we're going to calculate how much distance do we travel from point D. So other words, I know the velocity B, right? We know how much we have on the velocity B. We can break that velocity B 31.48 into by this 345 triangle into the horizontal component only, because I know that projectile motion from B to C, it's projectile motion. Projectile motion horizontally, we have constant speed, right? Horizontal component constant. So the 4 out of the 5, based on the triangle, 4 out of the 5 will be the horizontal component of that VB. And then multiply by time. All we got to do is figure out how much time does it take going from point B to point C. Now going to back to our projectile motion, we can use this equation to relating the velocity time together to figure out how much time does it take going from B to C. After we figure out the time, plug that back into that equation. That can help us calculate the horizontal distance. How much does it travel? Okay, hope that helps you. Last problem here. We have block A and block B. Okay, block A is got 60 pounds, block B is 40 pounds. Friction coefficient, kinetic friction coefficient between the block and the inclined plane is 0.1. We're going to look at the mass of the core and the pulley. Looking for the speed of the block A after block B moves 2 feet up the plane, starting from rest. Okay, we know that from the section that we learned about dependent motion, we write this equation. We know the total length of this cable does not change regardless how you're moving the A and the B, right? Total length does not change. We can write this equation, and we take the first derivative. That will give me a relationship between velocity A and velocity B. And then we're going to draw our free body diagram. And then we're going to do some on the y direction. We write our equation, right? We have the weight. Notice that for block A, notice for block A, I have 2 cable pulling block A. That's why when we're having this tension here, you have 2T. Okay. And they're sharing the same cable, the tension will be the same. But over here, A, you have 2 cable attached to it. That means 2T is pulling A. And then for that B, we only have 1T pulling it. Okay. Friction will always be the opposite direction of the movement. Normal force will always be perpendicular to the surface. We write our two free body diagram, or write our equations based on what we have on the free body diagram. Now, that's apply the principle of working energy. Principle of working energy, remember that we have 2 particles, 2 blocks in our system. We can put them together. Initial kinetic energy, when we say initial kinetic energy, that includes block A and block B, initial kinetic energy. And then how much work is being done, right, for A and B, right? So you have that for delta SA, you have all that for delta SB, okay? And then overall, we can, right hand side will be the final kinetic energy for, you see, VA2, and then over here, VB2. Now, because initially we are at rest, let's take a look again. Initially, we're starting from rest. That's why this term right here is going to be zero. That means initial kinetic energy will be zero. And the rest of them, really, what we just do is plug in what we know and then see what kind of unknown we have. One additional thing we'll be highlighting is that using this, right, the dependent motion that we studied in the previous chapter, we know that there's a relationship between the velocity A and the velocity B. Okay, so over here, when we plot it in, the velocity A and velocity B, we can, substitute VB in terms of VA. Okay, so overall, we really have only one unknown and calculating the result value of velocity VA2. Okay, that's all I want to share with you in this section. Hope you find this video helpful and thank you for watching.